There are some things I wanted to talk about computer hardware, and but I'm being deliberately realistic by saying that really none of it actually matters, except that some of it matters when it does, unless you're for example from Weka, in which it matters probably quite a lot. But I'm going to start with this is a kind of contrarian hot take, in that I think like computers are quite important. Obviously we use them every day to do our jobs, but do we actually need to understand them? Let's show of hands who's actually kind of like sat down and read a book about how computers work. Excellent. But there's a kind of Pareto principle in that you don't really actually need to know, say, how to implement a processor, which I actually was going to try and show some Verilog code on the screen, but I realized that would probably be quite a bad idea. But there's also even aside from productivity, it's interesting, which is a very like expletive-laden quote by the old editor of New Scientist, where someone asked him, why should we read your magazine? And his quote was basically along the lines of like, science is interesting, and if you disagree, you can something off. Yeah, but then the question then is basically how much to know. A couple of like key things, which we'll find out later, is basically one thing, i.e. memory performance. But there's also for the new programmer or someone new to a given architecture or type of computer. There's also the fact that the hardware implicitly provides an API, whereas based on kind of the way I'm talking, you probably think it's a performance talk, which it will be. But I also want to get this out of the way in that if you're, for example, new to computers entirely, you might be very confused by how floating point works, for example. But there are also systems which have completely different or more subtly different types of floating point, for example. So you have to be kind of aware of what you're actually dealing with. And this talk is also basically a superset of the things I said in the DConf Online talk. So if you want to know about how to profile decode, watch that one, because that's much more of a like, if in this situation, do that kind of methodological talk. So this is mainly things I either was sort of too stupid or too lazy to include in that one. But just kind of setting the stage. If we compile Hello World, like the compiler does sort of something, i.e. magic, it's another talk, turn them into instructions. It gets loaded into memory, and then we run it, and then something happens. The temptation would be just to talk about, for example, like as I mentioned, the API. That API also has a layout in memory. So, for example, that's an x86 instruction, which is quite useful to anyone who's ever benchmarked anything on x86, probably, which is it reads the timestamp counter, and the P means something else. But I'm going to try and avoid talking just about the kind of the semantics of the instruction sets, because it actually doesn't. It's part of the kind of the interesting stuff that comes outside of the 20% that gives you kind of 80% of the useful understanding. And I'm also given that it's a further along the API thing. We've just had Roy's talk, which basically covers everything I could have said about any multi-threaded code. Only far better than anything I could have said, because he's a domain expert. And there's another reason to not spend too much time talking about different differences between architectures, and that there's basically a handful of instructions that actually do sort of 99% of the work. Only in practice, it's closest sort of like the architecture overall will have maybe somewhere between sort of 50 and 200 instructions, which usually are there for a reason, even though there are some which kind of they're all equal, but some more equal than others. And that, for example, like ARM had an instruction just for accelerating JavaScript relatively recently, and x86 has somewhere between sort of 1,000 instructions, and I think if you include the whole lot, it might be closer to 5,000. It's 5,000 instructions, but it's a lot. So this is just a summary of what you actually might be running on, which is hopefully not new to anyone. Actually, has anyone run code on a RISC-V processor in the room? No one? Wow. Yes. But yeah, because they're kind of the new players. So x86 and ARM, everyone's pretty familiar with, but I think increasingly for geopolitical reasons rather than technical ones, I think RISC-V will be making an increasingly it'll have an increasingly large part of the industry, but it's already quite prevalent and sort of extremely cheap. Extremely cheap processors. And one thing I've also added right at the last minute, because it's come up a bit today, is that WASM up to this point in the talk is an instruction set. So even though there isn't WASM hardware, you still have the semantics, which are worth paying attention to. And it's also interesting because it's quite different to the way that the other architectures on this slide works. But that's kind of for a different talk. And another thing to be aware of is that if you port code from one architecture to another, there can be either instructions missing. So, for example, if you took like an x86 program and moved it onto a RISC-V processor, you might notice it might not have an into the divide instruction because it wasn't cost effective then to put it on the processor. Then there are actually some very dead but very interesting architectures that actually had no into divide entirely. But for anyone who's written SIMD code as well, you can notice there are differences in the instruction sets you have available. And I can't spell. There you go. But yes, if you ever have find a consistent illegal instruction, for example, you might be running like AVX code on a machine that doesn't have AVX, which is an x86 SIMD instruction set. And one thing I think is kind of interesting is that over time the processors that are actually on the market have mostly kind of homogenized. And one thing I found out, I think 6 hours ago, is that Intel actually made a really strange processor in the 80s, which actually had a garbage collector in hardware. That's the way to make everything D-friendly. And then Itanium, which came out I think when I was -1 years old, it had a very strange, very clever way of thinking about stuff. Only the cleverness was kind of in the completely wrong areas. So this is a good quote. We had a good team on paper, but unfortunately the game was played on grass. So, which is by Brian Clough, who's was a football manager. And the temptation is to kind of think like worse is better. But I think it's more that it's just the design. It just doesn't matter to the designers at all. And in line with the object-oriented part there, where there's a kind of hidden assumption throughout kind of all of this and all modern programming, in that we have virtual memory with a completely flat address space, which actually hasn't always been true, which isn't just in reference to x86 segmented memory, because that was horrible, but there actually have been different takes on it, which are very interesting and are I think all dead, unless you're running mainframe code from like the early 60s. The thing to be aware of is that the hardware is only as good as we can actually use it, and it's designed around the patterns that are actually in modern code. There's kind of a lot of literature on how much, like kind of in the abstract, how much performance you can actually get from the typical code that sort of the human being might write. And one thing I noticed when I read this is that if you say sort of for the purposes of this that performance number is 3 performances, the upper bound people estimate that seems to vary from like 3 to like 10 to 500 to 1,000, so maybe it isn't bounded. This is an important part here, and that if you think about basically any D program, like how many lines of code are there between any given kind of bit of control flow, which is like boils down to in like the typical numbers that you actually get out of the compiler, instructions. It's basically a handful, which is one of the reasons why architectures like Itanium died, because it was effectively looking for code that's kind of very, very regular and doesn't think much effectively, and that we spend a lot of time in loops. But I mentioned this earlier, but the central kind of thing to be aware of is memory performance. Oh, actually, I forgot to say, please ask questions if you have any. I'd like the distraction. Yeah, but there's a quite famous computer architecture paper called "It's the Memory Stupid," which was published in 1996, where Richard Seitz, who is an architect at DEC, which is the Digital Equipment Corporation, he was the architect on the DEC Alpha, which still today is a very, very impressive processor. He made projections on processor speed and the memory performance, and estimated that effectively no matter how kind of clever the processor is, there just won't be enough memory performance to actually tell it what to do fast enough. And he actually made a fairly conservative estimate, and today is actually worse than the paper, which is quite hard to find because it's in a review paper. So there's lots of people referencing the paper, but actually finding the paper is quite hard. But this is the kind of the key takeaway of kind of the entire talk, or just sort of modern computing in general, which is that memory performance is the performance. One thing you can do if you go to that link there is you can actually run a memory latency test in your browser because it uses JavaScript. But the thing to kind of be aware of, and we'll talk about why in a little bit, is that can everyone see right at the bottom? You might have to look at the things at the side if you can't. But you have very fast memory up to a certain amount of kind of memory that's currently in play. Then it's okay, and then it's genuinely terrible. One subtle thing as well is that if you're on either on a phone or writing code for a kind of a bigger than a microcontroller, but not a kind of general purpose chip, is that when you're in kind of this region here, this also the energy usage is also quite high, so you need to kind of pay attention to that. The ideal way, the memory is very slow, so we want to put a cache in front of it, which is obviously this is kind of evidence of that. But ideally, we want a cache which is basically infinitely large, can do infinite amounts of stuff at the same time, responds instantly, is persistent, and is very low cost. Now, obviously, like intuitively, that we can't have all of this, but you can actually get surprisingly close if you have a kind of somewhat competently designed program, which is actually turns out very few. But if you imagine like you can get if I hit the cache on this laptop, I can get it in 20 cycles, which is basically like not many nanoseconds, up to something like 12 megabytes, which is like just astonishingly good. One thing we can do is to kind of think about certain, because we can't have, for example, we can't have infinite capacity or infinite bandwidth, so we can find side effects from having finite capacity and the way the caches are actually designed, and from that we can derive like some ways to write code that's aware of that. So if you fall asleep, just locality, that's the word. If we have a large array and then we just walk across it, like starting off by just byte by byte, and then we go from maybe like for every 4 bytes, every 8 bytes, etc., etc. The access time per access as we go across, it isn't flat. In fact, it's actually so much slower that it's cut the bottom of the graph off. But if you imagine down there is where it's supposed to be, and then we hit 128 bytes there, and this is a log scale, bear in mind, so that's really bad. That's the size of the cache line, because you can't if you're going to build a cache, you can't just do it in terms of bytes because there's just too many of them. So you pick some size in which the cache will kind of, when it moves things around, and that's its kind of unit of granularity. And the conclusion is that when we get to a certain size, we're on this side, and the kind of like the happy bit, we're accessing one cache line. So we're still in the same cache line for every stride. But then on, past here, we're hitting the next cache line, which is why it's significantly slower. One thing to keep in mind with the cache lines is that if something is actually in the cache, it's actually unless you're doing this and kind of deliberately being irritating, you can it won't just be like this is in the cache and then the ones adjacent to it won't be. It's actually normally it'll fetch like something on the order of like 10 at a time. But back to this like memory latency graph, we can see the cache has multiple layers, and that if you see there's 256K there, that's that kind of just beginning of the spike is just there's a spike, which is where the working set gets too large for the level 1 cache. So we're now starting to hit the level 2. The reason why it's a curve is a combination of some of the memory being in one level and the other, and I think there's also some interaction with the TLB that I don't understand. When you do memory accesses, the CPU is actually constantly looking for patterns that it can exploit. So for example, in this strided example, the CPU will have spotted the stride with something called a stride predictor, and then it will start prefetching further and further and further ahead. The more confident it is, but you can actually do this. You can force it, because we have prefetching intrinsics in core.sim field. I'd recommend thinking quite hard before using them. As I mentioned earlier, if we have virtual memory, we have to have a way of mapping the virtual memory that we access to the physical memory that's actually installed in the RAM. There's actually the RAM that exists in reality, which is all dictated by the OS. The implication of this is that the CPU has to be just constantly walking, basically just keeping track on the mapping from X to Y all the time, which is why one thing I'd just like to note is that with the default on a lot of systems is still basically for a 4 kilobyte page, which if you imagine, I think like an iPhone, the top of the line iPhone has 6 gigabytes of RAM. That's like millions of pages, which is why huge pages were invented. So you have a larger page size, but the reason why I'm noting this now is that normally you can have a transparent huge page, which in theory will just be handled by the operating system. You just magically get a sort of more efficient page tables, but that actually isn't always true. So if you're like writing a memory allocator, you can actually specifically ask for certain types of pages. As I said earlier, this is all really expensive. So you have a cache inside the processor which keeps track of all of this, called a translation look-aside buffer, which is actually that's actually the first cache ever to be implemented in hardware. I think it's the first thing that you recognize as a modern cache. Was on a computer called Atlas II, which I think was it was a British computer from the 1960s, built by Ferranti. And this is the textbook cache-aware transformation AOS to SOA. We're going from an array of structs to a structured array, and like Dennis mentioned this right at the end, where if you imagine we have some kind of data that we want to store, but we know that we're again I can't spell. But we know the access patterns, and we know that we're going to access, say, all of the X's, then all of the Y's in one, but then all of the Z's, or sorry, Z's. It can be very profitable to transform this to this form underneath, where if you imagine, rather than hitting, say, like one byte in every whatever the overall size is when we've laid them out, we're now accessing 100% of the cache line every time, which is much more efficient. This part of the talk was originally going to be kind of more on like how bits of the back end of the processor actually works, but I've kind of decided against it because it basically doesn't matter relative to all the memory stuff I've mentioned. If you notice here, this has 10 approaching 20 pipelines. Well, each one of these does some tasks. We have your arithmetic logic units that do maths. Then for example, AGU is an address generation unit. This is all very wide at the back, whereas the thing which they struggle with is actually just keeping it fed with actually stuff to do. And the thing to Google for is how they work is, I think it's restricted data flow, which is the kind of the academic term for going from a kind of like ideal parallel execution of the available work you have, and then condensing that into something which you can actually turn into a chip. As I said earlier, the average length of a basic block, i.e. between the if and the do something else, is very small, and the solution is to just guess, i.e. it does branch prediction. If you imagine you have a loop, for example, the kind of static branch prediction, so it has no knowledge of it doesn't acquire any knowledge about the program at runtime. where, for example, if the branch is going back up the code, then you guess that it's going to, and then if it's going forward, then you guess it's not. That's enough to get something like 75%, get it right 75% of the time on kind of standard benchmarks. And one thing, just because I've had arguments with this about people, is that like static branch prediction doesn't actually really exist in the wild anymore on kind of modern like top of the line processors. So you can see a lot of arguments where people are talking about like the pipeline when that pipeline doesn't actually exist, because it's just sort of made up, because it's yeah. So just kind of be careful about that, because the reason why is that the static branch prediction actually would have to happen far too late in that pipeline, which is why the dynamic approach is preferred, because you can guess much more aggressively if you actually just don't pay any attention to what the branch actually is in how it's written down. And the way to get the extra kind of 25% is to learn at runtime. And I actually checked this earlier, and I think the current AMD branch predictor that they're shipping in their current processors is getting like something like high 90% now on things like kind of compression benchmarks and things like that. So it's extremely impressive, because if they effectively have what's a little bit like a neural network inside, which I wanted to cover, but I don't understand it. So yeah. But the far like nastier, the kind of like the insidious type of branching is any kind of like chasing around indirections. It's like function pointers and virtual calls, et cetera, where there's actually an entirely separate set of caches called branch target buffers, which also have their own kind of specific structure, like the data caches. Where the idea is to say, if you have like an interface which is then implemented by 3 different classes, there'll be 3 different places that it can jump to. So it can store the locations of the various foos in the executable, and then make a guess which one, and then start executing it before it actually happens. Which brings me on to like Spectre and Meltdown are the reasons why everyone's computers got slower 4 years ago. Because everything's dominated by memory performance, if you want to speculate anything, you have to be able to do speculative memory accesses, which means that there's some researchers actually discovered that you can use some clever side channel attacks to effectively extract data from the program based on code that is never actually run, because you can just trick the processor into running it. So Spectre will be with us for many years, whereas Meltdown, which is the really bad one, was where Intel basically forgot to implement the check, where they would speculatively make memory accesses to locations that weren't actually part of the program's memory. So it's the equivalent of like just letting you read anywhere in the address, but the physical address space is memory, so you could just extract all of the encryption keys in the system, for example, which is why kind of people were panicking. But we kind of got away with it in the end. The one thing that is actually kind of exciting at the moment is that now kind of like everyone's on the AI gravy train. It's a workload that's extremely well suited to basically new types of computer architectures. So for example, does anyone use a Google TPU to do machine learning? No. But they've designed these tensor processing units, which are effectively AI accelerators, and you can rent them on from Google's cloud, which is a basically completely bespoke architecture. And then because of that, we now have new types of instruction sets being implemented. So for example, Intel have these vector neural network instructions, and Apple have some things as well. And these all work like fairly trivially from D, even before the compilers actually know they exist, because you can, like, one of the nice things you can do with it, you can just generate the assembly using CTFE, and it just sort of works, which is nice. And speaking of which, we have GPUs, which I wanted to talk about, but I didn't know how to make it flow. Yeah. But the thing there is decompute, where at some point we need to kind of re-implement PyTorch with D, because yeah. See and that's it. So, but I think I'm massively under time, so you get to have a longer break. So yeah, any questions?
Cheers. So a few years ago, there was this promise that we were going to be scaling up multiprocessors and just go up to like thousands of cores and all that crazy stuff. And then that sort of died by virtue of we had absolutely no way to keep those cores fed to some extent, and we also didn't have any applications that could really profit from that. So I think a lot of that went into GPUs. And as someone who is a fan of ray tracing, like GPUs are good for ray tracing now that they have hardware support, but like if you wanted really symbolic ray tracing with like not very many triangles and so, but you have a lot of branches, then you're again out of the field that GPUs are suitable for. So do you think there's any architecture where we're ever going to see that sort of like highly branching code on lots of small cores operating on small data sets?
Well, I would say no in case I'm wrong, but there, I mean, there was a DARPA-funded RISC-V processor, which is in the kind of like thousands of cores model. But the thing is, with these kind of bespoke systems, a lot of the time they're basically built for a specific use case. So, I don't know. Specifically with ray tracing, I've written a ray tracer, but I've never written a good ray tracer, so I couldn't say.
A few years ago, I was listening to a lecture. I'm not sure who it was by, but I think it's one of the famous computer science professors who said that from the 60s to the late 2010s, a processor could touch all of memory in about a second. And this relationship had held since the 60s to the 2010s. So I wonder if this is still true. And does it scale across all devices? So for example,
I don't know, we can find out later by just writing a program. But the thing is, it's not so much touching the memory is actually because as I said, if you have a well-written program, you can actually fit in the cache relatively easy. So it's a common thing if you like really like performance tuning something to just measure the working set. But it's just you have these. There's the kind of like the happy period of the happy part of the graph, and then when you leave that sort of like things get really horrible. But I don't know. But like the thing with memory. It's not so much actually like hitting it as much as the power consumption from having lots of memory is quite terrible. So actually one thing is kind of interesting is that in this if you imagine in like a CPU you have like say like 8 or what 8 like 16 of these, they all have to be connected over an interconnect, and the interconnect is usually just like some kind of 1 pixel line on the diagram, but the interconnect itself is actually where a huge amount of the power consumption of the processor comes from. So what we'll probably see, or at least a lot of people want to see, I have no idea whether it's going to happen or not, is sort of in or near memory computing. So you actually have sort of dumb processing outside the CPU, but closer to the memory, which is would be nice to see. But you have had the opposite approach as well, and that just because it helps them scale. Like this is a like M1 processor, and it has all the memory on die shared between. Actually, no, sorry, it's not on die. The memory is very nearby to the CPU, and it's shared with the GPU as well. Yeah. But in response to the original thing, I assume it hasn't changed too much to the how long it would take to walk all the memory, because memory bandwidth has actually kept going. It's memory latency that's particularly terrible.
Yeah, and I think also that the problem in modern processes is that the clock tree is, if you want to try to make something synchronous, then it takes like 60 to 70% of the power.
Yeah.
So in principle, you don't want to make synchronous big processes. You want to make something like network on chip or something, right? And I also think that processes tend, if you want, as he said, if you want to have thousands of processes, you will probably have a process which is more simple, and then have many of them, and then clock them at a lower frequency, because, yeah, the power is to the square of the frequency, right? So you will probably just reduce the speed and have many of them. So you will also reduce the problem with the dark silicon problem. So.
Yep. One more question?
Well, we can take a few more than one.
Well, no, so I said, as in there didn't seem to be many before.
Yeah, one thing that actually surprised me earlier, like a few years ago when I found out about this, is that we are now at a speed of a system where the physical distance between the processor and the memory actually has a significant impact on performance. Like you can sort of, if you look at the units of light spreading, and it's not even at light speed, it's lower than light speed, but like in a modern clock cycle, like the actual electrical signal can actually not get that fast. And so like, I've been waiting for a long time, and they're now starting to do stuff like stacking memory on top of processors. But how far do you think that can practically go? Like how many slices can we get up?
Well, I think that's a question for people who like work for who actually work kind of on have the kind of skin in the game, rather than me. But like I think AMD is supposed to be shipping the vertical cache thing soon. Which should be a nice increase, but I think the it's gonna have to happen. But like it's the way the fabrication processes are already like just unbelievably complicated at the moment. So I don't even want to know what it would be like with like three-dimensional chips. But yeah, maybe ask me in 10 years. I don't know.
So what would be some ways that programmers can avoid all these traps and
watch my talk from DConf Online, because like this is kind of the kind of more like kind of waffly bits that I kind of forgot to mention. But I gave like specific examples of spotting how to specific examples of spotting kind of particularly bad kind of like cache access patterns with like VTune, for example, or like AMD have a sort of a crap version of VTune called MicroProf. So if you're on AMD, you have to use that. But like it's better than nothing. Or on Linux, you can use Perf, which is supposed to be architecture independent.
But some obvious wrong things, like you mentioned interfaces and pointers and indexes, that kind of stuff.
Well, not really, because it's the same. It's kind of like where's my structure erase bit? Oh, did I go past it? Yeah. So with this kind of thing, like you might think, like it's automatically going to be faster, because it's a popular thing. A lot of people are aware of the transformation. But like if you do access them all at the same, this is actually probably why X, Y, and Z is probably quite a bad example, because you probably do access them quite regularly if you imagine their coordinates. Like if you are going to access them together, then you're not going to see the speed up. So like it's a question where it has to be like dictated relative to the program that you're actually writing, rather than kind of just like if this do that, because otherwise there'd be no need for programmers.
Thank you. Mine is a very silly question. What does it mean static in the static jump prediction?
It just means that the rule is independent of any of the previous behavior in the program. So there's no. So if you have a dynamic one, it has basically a cache of let's say like counters where it can either sort of add one or subtract one depending on what's happened before in the past, and it will keep track of the history as well. Whereas with a static predictor, it's just a rule that the processor designer chose that could be sort of simply implemented without having to keep track of any history.
But it keeps tracks at least of the last jump, probably.
Well, no, the static is solely dependent on where the branch is to, and where it is in the program.
Oh, so it doesn't consider even the last.
No.
Oh, okay.
But doing like whatever you did last
so
is very, very effective as well.
I didn't know it
Like dynamic
ever
prediction.
existed. That's
Yeah.
What static branches did was, since most branches are for loops, most branches are jumping backwards. And so the prediction was the jump would go backwards, and that's what static branching is.
Yep.
All right, I think we can do one more question. One more question. There we go.
So you mentioned that some programmers, try to optimize their code based on some incorrect, intuition of how the CPU pipeline works. Do you think there's actually like a better mental model, like an intuition of the modern pipeline that is useful when writing performance-sensitive code, or should we just pretend it's magic and not try to understand it?
Well, firstly, you have to actually profile it and make measurements, like controversially. Intel have either Intel or someone who works for Intel has a acronym called TMAM, which I think is top-down microarchitecture analysis methodology. And that's basically a graphical representation of where the process is spending its time. So again, watch my previous talk, because I spoke about it a bit in that. Because like VTune will actually, rather than just showing you a bunch of just like throwing data at you, VTune will actually basically draw a pretty picture of where the process is spending its time and where it's bottlenecked. In fact, if you've read Andre's blog post from I think 2018, which is the like Lomyato's comeback about partitioning in quicksort, the diagram from VTune that he uses there is from that methodology. So that's a kind of practical example combined with some sort of smart algorithm stuff.
I remember reading that, but it's been a while, so maybe we should revisit it. Thank you.
Yeah.
Okay, and that's it for question time. Thank you again, Max.